This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
What types of problems do civil, geotechnical, other types of engineers solve with these trucks? Like, what are those grand research questions that they're built to answer?
Yeah, so we have a science plan where we kind of have three major categories of research that we use these trucks, uh, to solve problems of engineering interest to society. And I actually, probably the best way to show this is to share my screen, if that's okay.
Yeah, go for it.
Because I have a couple of videos I think that will help, or animations that will help describe what's going on. So I'm going to hit share my screen, and hopefully this works. There we go.
Awesome, got it.
Great. So the three areas that we use these trucks for most often, they're not the only things we use them for, but the three main areas have to do with subsurface imaging. So trying to develop 1D, 2D, 3D images of the subsurface. And I'm going to activate this video here. This application illustrated in the video animation is imaging of a levee. So, for example, we have thousands of miles of levees in our country where we really don't know how they were built historically. We don't have good records. And on occasion, when it floods, or possibly in an earthquake, if there is soil liquefaction, sections of these levees could fail. And when that happens, there's a lot of flooding and really dire consequences associated with that. But because we have so many miles of levees, we can't rely on traditional site characterization methods to scan and look for these weak zones. So, for example, we're working on ways to profile or image these levees by maybe towing sensors along behind the truck, shaking the ground, and trying to develop these scans or these images of the subsurface. And we're moving towards 3D site characterization, what we call full waveform inversion. That's a big topic in the future. So we use the trucks as a source for waves to probe or image the subsurface.
So you've got places like in this video, you had an example from New Orleans. I remember a few years ago, we did a workshop in St. Louis at a levee nearby. And these are, I mean, if anybody's been to New Orleans or knows anybody who's been down there, that's a big deal when those levees fail. I mean, that's what happened during Hurricane Katrina and caused billions of dollars of damage. And what it sounds like your team is doing, the Shaker Truck team is doing, is being able to say, hey, let's keep that from happening again. Let's look at what we've got. Let's no judgment on whoever built these. I'm sure they did it the best they could.
Yep.
But here's where we're at now. And if a hazard event happens, it doesn't become a disaster unless there's something built there to affect, right?
Right.
And so we're looking to take an honest assessment of what's there and be able to make an improvement if we can, so that a hazard event doesn't become a disaster. If I'm hearing you right.
That's exactly right.
Cool.
The second area that we focus on is, we call this nonlinear in situ testing, kind of some technical words, but we push sensors into the ground. So in this previous application, we're only keeping our sensors on the ground surface. In this type of testing, we're actually using a hydraulic ram on the back of the truck to push sensors in. So we push pore water pressure transducers, we push accelerometers or geophones into the ground, and then we shake the soil and we try and monitor the response of the soil. And we would do that to study soil liquefaction. So for example, we could go to a site and we could test the ground and try and determine how susceptible that ground is to liquefaction during an earthquake. And we've used this technique up in Portland not too long ago, where we were testing silty soils, which are really hard to characterize in the lab, but also bio-improved soils, where the researchers have used either precipitation from biological organisms that would cement the soil together or even desaturate it and cause, air voids in the soil, which would help prevent it from liquefying. So this is, one application where we've looked at nonlinear testing ranging from small strains up to large strains to characterize, for example, soil liquefaction.
Awesome. Yeah, well, if you're a longtime listener of the show, we had one of the researchers from I think it was Portland State University
Yeah.
up in Oregon, talking about those biomediation methods, and that test that you guys did up there. It was fascinating to hear about just what you're able to do with, at least on the order of magnitude, fairly affordably mitigate liquefaction, like compared to traditional methods where you might be, putting big posts or pillars in the ground or relocating buildings or what have you.
Yeah, and that's one of the interesting aspects of our site. We're somewhat unique in that we're not confined to a lab. We believe that there's obviously a lot of great research and things that can be done in labs with scaled down models and testing. But ultimately, at the end of the day, we need to implement these methods on real projects, real sites, full scale. And that's one of the cool things that we have the opportunity to do by taking our shaker trucks to excite, structures and real soil deposits in situ. That kind
And
of
you may
brings us
be
to,
able to, and I think you guys have done this on a number of occasions. Of, a researcher wants to study a particular site and make some improvement to it. They'll have a soil characterization, cycle done. They'll make a scale model of a structure and the soil profile and put that at the geotechnical centrifuge at our friends at UC Davis. Make sure that it matches the full scale, do some sort of improvement or build something, and then they'll be able to bring that full scale, having validated it in the lab. Is that kind of how things go with you guys?
absolutely, yeah, it's good to work on, putting all the pieces of the puzzle together from in situ to smaller or lab scale versions, or using the centrifuge to scale up models, because each piece uh, is important to putting the whole puzzle together to see the big picture and making sure that your designs are as good as possible.
Yeah. And so in your video here, you've got a little bit of a scale on there, but for those who don't have the advantage of YouTube, how far down are you putting these sensors?
So depending on the testing configuration, it might be within several meters of the subsurface. So let's say the top 10 feet, but it could be deeper. It could go down to, 8 to 10 meters. So
Oh wow.
approaching 30 feet perhaps. And that's about as deep as we've done this so far. And that's just because we're limited on how large of strains we can develop in the
Okay.
ground. And what's shown here is we have what's called a drilled shaft or a drilled pier. This is a concrete uh, pile that's been installed in the ground. And then if we shake on top of it, we can carry these large strain waves deeper into the soil.
Wow.
Otherwise, if we step back a little bit, we might be shaking just right on the ground surface and testing soils that were closer to the surface.
Oh, okay. Cool.
Yep. So the last of the three major areas we're studying is structural health monitoring and soil structure interaction, where we would use our shaker trucks and associated instrumentation, different sensors, and put them, for example, on a bridge. And then we could move the truck around on the bridge and shake in different locations and have a really controllable source in terms of its amplitude, but also its frequency range. And we can shake not just on the structure, but we could, for example, pull around and shake on the ground away from the bridge or the building, and we could send waves through the soil into the structure,
Oh wow.
which allows us to study what we call soil structure interaction. Again, in a rough sense, simulating waves that would be traveling from an earthquake through the ground impacting the foundations of the structure, getting carried into the structure through the foundations, and then exciting, in this case, a bridge.
Now, this is a really hot topic in civil engineering, just especially in the United States. Our bridge infrastructure is woefully inadequate in a lot of places, and you've heard, if you've been in this world for any length of time, just study after study of the decay of our bridge infrastructure, and it sounds like what you guys are doing are one way to be able to truly characterize the level of decay of a particular bridge, and is it still adequate to carry the loads it was designed for, and things like that.
Yeah,
Is that
you
right?
bet. You bet. A lot of our bridge inspections right now are, we rely on visual inspections, and in many cases, you could miss things that might be decaying or causing problems, whether that's under just static gravity loads or whether the dynamic loads of a large earthquake. So, as we move forward in our future, we'll definitely be instrumenting more and more bridges, either with permanent or temporary instrumentation, and we'll be using dynamic methods to assess their abilities to carry loads and perform under extreme loading conditions like seismic events.
Wow. Yeah, it's amazing the variety of applications that you have for these very uh, unique instruments. It's really cool.
Yeah, we enjoy it. It's pretty fun to be able to travel around the U.S. and around the world and take these trucks to work with researchers from many different universities and get to study and work on problems of interest to them and to our society.
Yeah, you mentioned the being able to deploy to Christchurch a few years back. Can you tell us about that? That was, I mean, just some of the videos that were coming out of that and the research coming out was just incredible. It sounds like a really interesting story.
It was. We went to New Zealand after the Canterbury earthquake sequence or the Christchurch earthquake to do two main projects. One regarding deep subsurface imaging, where we were trying to really look deep into the ground because the soils in Christchurch are very, very deep, more than, let's say, a kilometer or 3,000 feet
Wow.
down to bedrock in many cases. And there's no economical way to drill borings that deep. We can drill that deep, but it's really expensive.
Yeah.
So we were going down there trying to help them develop profiles of the ground beneath all of their strong motion stations that recorded the earthquake
Oh wow.
so that we could build numerical models that would allow us to try and calibrate these models to be able to better predict the shaking that was recorded. We
Mm-hmm.
call that a backward analysis. So we
Mm-hmm.
wanted to do this backward analysis to make sure that we could predict the levels of shaking that were actually recorded in the earthquake so that we felt comfortable then doing forward analyses or design in the future where we're like, look, we now have a calibrated model and we know that it's accurate and we can use that model now to better predict what levels of shaking will happen in future earthquakes so that we can design our our bridges, our buildings, our infrastructure like our pipelines to resist the shaking.
Mm.
So that was one project. The second project was related to the just pervasive soil liquefaction that happened. And in particular, we were studying a problem related to how to come up with economical solutions to mitigate soil liquefaction for residential structures.
Oh wow.
In Christchurch, after the earthquakes, they had to basically abandon 10,000 residential properties
Whoa.
and did not, they basically tore down all of those homes and forced 10,000 families to leave. And we were trying to help a partnership between the US National Science Foundation and the government of New Zealand, trying to come up with economical ways to mitigate liquefaction using various ground improvement techniques.
Mm-hmm.
So the contractors in New Zealand would install these different ground improvement methods, and then we would use T-Rex to shake those ground improvement measures and determine which ones were most effective. And then, of course, we would look at the economics of, which ones were both effective and economical.
Yeah.
So that was kind of the second major project that we used.
What did you guys find there?
So we found that there were a number of ground improvement methods that worked, and it depended on if you were trying to improve ground beneath an existing structure, like what would you do, versus if you have what we call a greenfield site where it's a brand new piece of land and you're going to go and improve it before you build structures on it.
Okay.
So we found that some of the methods worked better than others. I probably won't get into the details here in this podcast. And also, some of them were more expensive than others.
Yeah.
And so we gave people kind of a range of choices that they could look into in terms of cost and effectiveness. And we did find some things that were shown not to work very well. And what we did there was, just like we showed in one of those videos previously, we were pushing the instruments into the ground and then shaking on top of the improved and the native soils to compare, how much the soil was improved against liquefaction.
That's awesome. We'll have to get with our team and see if we can link to some of those videos that you have there. You've got a T-Rex was actually creating liquefaction at some points, and you see water bubbling up, and it was really cool.
Yeah, it was a big project and a lot of interesting work for sure.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.